I think.
Just a second, I will confirm that. Okay, we can start.
Okay. Okay.
I can start?
Yes. Yes.
Okay.
Yes, please.
Okay, so thank you. Thank you to you for the invitation. I am happy to be there, IEP formally. So my talk today it will be quite simple, and I will speak about basic problem like the correspondence principle and quantum mechanics and correspondence principle, and also the relation between instability and chaos in quantum mechanics. So the talk it is quite general in nature, and so it should be quite simple. So first let me, let me start with a few words about classical chaos. Now, you already know about this, but maybe it's good to remember some points. So as you know, dynamical chaos destroys the deterministic image of classical physics, and the deterministic trajectories are in some sense random and unpredictable. And this kind of behavior is rooted in the exponential instability of motion, which is seen if you linearize the equation of motion and write this linear equation, or delta Q or delta P are n-dimensional vector in tangent space. So these are the linearized equation of motion. And so these equations are linear, but you cannot solve because these coefficients are computed on the reference orbit around which you linearize the equation. And so this depends on time. So they're linear equation, but they're time dependent. So obviously you cannot solve in general analytically. So now if you look at the tangent vector, delta Q, delta P, okay. And then you compute the length of this vector, square root delta Q square, delta P square. So you compute the length of this vector and take the logarithm divided by time, let t goes to infinite, and you get the Lyapunov exponent, yeah? So if this is positive, it means that the system is exponentially unstable. The reason why the motion which is exponentially unstable is called chaotic, it is because according to the algorithmic theory of dynamical system, the information I of t, which is associated with the segment of trajectories of length t, is asymptotically given by this. So this quantity, which is positive, it divided t in the limit is some quantity h, which is ks entropy, which is positive. So it is chaotic because in order to predict a new segment of a chaotic trajectory, you need an additional information which is proportional to the length of this segment, independent of the previous length of the trajectory. So in this sense, exponentially unstable systems are called chaotic. And you need exponential stability, yeah, because as it is written here, if the instability instead of exponential will be only power law, then the required information per unit time become inversely proportional to the previous length of the trajectory, and therefore asymptotically prediction become possible. So chaos, this is the reason why chaos, the word chaos is associated to exponential stability. Basically what you can do, you can, I don't know, you can go back up. Let me see, oops. Okay, so you can define a parameter R, which is lambda is the Lyapunov exponent, t is time, mu is the accuracy at which a trajectory is recorded. So it is important this parameter R. If this is much less than 1, then prediction is possible inside this region, with this parameter less than 1. But when this parameter is larger than 1, then the motion is not distinguishable from a completely random motion. Yeah. Well, this is just an observation because sometimes it may lead to confusion because the notion of exponential instability, I mean, the condition lambda greater than 0, I mean, exponentially stable motion is not invariant under time reversible of time variable. For example, if you take this relation, which is an example of completely simple linear motion, predictable motion, phi equal omega t plus phi 0. If you make a logarithmic change of time, if you introduce a discrete time n and this variable beta n, omega tn, then this equation, this relation becomes this one. And this is typical for a random process. Multiplication by 2 leads to a completely chaotic sequence. So just want to notice that you must be careful not to choose. You are not free to choose any time you want. Yeah, you must take the proper time of the system because this property is not invariant under change of time variable. Okay, so in classical mechanics, just to make a summary, there is a complete theory, fairly complete theory, which is called Ergodi Theory, which goes from one extreme of completely interval systems, a system with n degrees of freedom, with n constant of the motion, and these systems are characterized by discrete spectrum of the motion, I mean, they have discrete frequency, and the motion is only linearly unstable. At the opposite end of the ergodic hierarchy, there are systems with random, the random system with positively a Punov exponent. And in between, there are several properties which are characterized by Ergodi Theory, the systems which are KM integrable, ergodic system, weakly mixing, and so on with different statistical properties. So I don't enter in this discussion, but just to say that in classical mechanics, we have a fairly complete theory of statistical property. And basically, you have example of this. For example, if you take a billiard in a circle, this is an example of a system which is completely integrable. You have 2 degrees of freedom, and you have 2 constants of the motion. And then there is opposite side, there is a billiard in a stadium, which is completely chaotic with positively a Punov exponent, so there is exponential instability. And in between, we have systems which are KM systems which are only ergodic or ergodic and mixing, like billiard in a triangle and so on. So these are examples of systems which belong to different category of classical ergodic theory. Okay. Well, another observation is that the classical description also important that instead of orbits, trajectory, you can use distribution function, as you know, and distribution function obey the linear Liouville equation. I remark this because sometimes one hear that, well, quantum mechanics, there is no chaos because the ordinary equation is linear and so on. So, but this is not the point. Yeah, nonlinearity, even in classical mechanics, refers to the orbits, to the trajectory only. Yeah, the Liouville equation is linear, like the Schrödinger equation, but still you can have chaos, obviously, in classical mechanics. And mixing is a property which leads to the statistical relaxation to the steady state. And you must notice that the relaxation process is time reversible as it is for the trajectories. Both trajectories and the relaxation process is reversible in time. However, and here's the difference, the motion, the relaxation is non-recurrent. Yeah, contrary to the motion on trajectory, whether integrable or chaotic, it doesn't matter, always recur, and recurs, not only recur, but it recurs infinite many times. Yeah? And for chaotic system, even the recurrence time is not bounded from above. While for integrable system, it is bounded, but always recur due to Poincaré theorem. Okay, then so this is about classical, this is about introduction about classical ergodic theory. but I want to notice that this theory, we have this theory only for systems with finite number of degrees of freedom. But we don't have so far at the moment a theory for infinite system, like for example, when you have field matter interaction. And this is because the two limits, T to infinite and number of degrees of freedom to infinite, they do not commute. So the theory, we don't have a theory for this, and it would be nice to have such a theory. And in this connection, let me mention, this is a quotation by Max Jammer in the book, The Conceptual Development of Quantum Mechanics. He stated in the introduction that quantum theory had its origin in the inability of classical physics to account for the observed energy distribution of the blackbody radiation. It was unfortunate that this was the first problem dealt with in the systematic development of quantum theory. Yeah, because this problem is quite complex. And I take this occasion to put to your attention a recent paper of us, which was published this month, in which we discuss just this problem. We discuss the problem of blackbody radiation from the point of view of classical mechanics. Yeah. So maybe if you give a look at this paper, maybe if you have some question, maybe you can write to me and we can discuss it. Then also the problem is when we have Ergodi theory for a classical system, namely when h bar equals 0. The question is that we do not have Ergodi theory for finite h bar, mainly for quantum system. And again, the difficulty here is again that the two limit T to infinite h bar go to 0 do not commute. So this is another difficulty. We don't have a theory, and this is somehow is the subject of my talk today. It will be this case. And then more complicated case is quantum system with infinite degrees of freedom, from which, as far as I know, there is almost nothing known, at least to me. Okay, and so now about quantum chaos. Again, I think that you already know, quantum chaos is an attempt to understand classical chaos in terms of quantum mechanics. And the difficulty, as you see, in a clear way is the following, because I told you about classical Ergodi theory. There are two extreme situations, integrable and chaotic. So an integral system are characterized by discrete spectrum of the motion, by linear instability, by quasi-periodicity. Opposite case is chaotic limit, in which the spectrum is not discrete but continuum, the instability is not linear but exponentially, and there is no quasi-periodicity, there is approach to equilibrium, and so we have true chaos. Now, the point is that quantum mechanics, with finite degrees of freedom again, as we know, the spectrum is always discrete, no matter whether it is integral or chaotic, is always discrete and quasi-periodic. So at first sight, it looks like that it is always like the property of the classical integral system. So indeed, if, for example, if you consider the simple case, to a string case, the circle and the stadium, so classical systems are completely different, integral and chaotic, so completely different motion. But the quantum motion is quite similar, because in both cases you have eigenvalue and eigenfunction here, we have eigenvalue and eigenfunction, and in both cases the solution, psi of t you write in this way. Yeah. So it is quasi-periodic in time, almost recurrent, and so on. So this may raise the question, well, then there cannot be chaos in quantum mechanics. On the other hand, the problem is that there is a correspondence principle which require transition from quantum to classical mechanics for all phenomena, including dynamical chaos. So how you reconcile these two aspects? Okay, so the answer we've given long ago is that the distinction between discrete and continuous spectrum becomes sharp only in the limit T to infinite. And for finite time, quantum system possesses all the property of classical dynamical system, but only for finite time. And this time go to infinite, S bar go to 0. So you recover chaotic classical motion. So quantum chaos, in some sense, reconcile these two apparently opposite regime, regular and chaotic, in the general theory of dynamical systems. Okay, so as I say, exponential instability is at the root of chaos in classical mechanics, and it is possible to show that in quantum mechanics you have exponential instability like in classical mechanics, but only for short time, only to time up to a time which is called Ehrenfest time, which is order logarithm of h bar. So it is very short. Nevertheless, as you let h bar go to 0, this time goes to infinite. So you require transition to classical mechanics as required by the correspondence principle. So okay, up to now is okay, but now there is a point I want to discuss today because very recently, a couple of years ago, appeared an interesting paper by Bunimovich, for the Bunimovich Stadium, Galinsky and Rosenbaum in PRL, in which these are taken from the abstract. This result suggests that classical to quantum correspondence in dynamics is violated in the OTOC. OTOC is out of order time correlator, which I will introduce, which you know, but I will recall now. But basically what they do, they consider a billiard in a polygon. Now a polygon in classical mechanics, it is known to have 0 Lyapunov exponent. The instability is only linear, not exponential. But they quantize a polygon and they found exponential instability, and this exponential instability persists in the limit h bar go to 0. So this is clear violation of correspondence principle. So this is the result of this paper, which is very surprising, which I want to discuss today. And also in the same, basically the same month, another paper appeared, this one by people in Berkeley, in which they say that they have this word scrambling. Scrambling, I don't know, people like now use this word. It's just, in Ergodi Theory, it is called mixing. So I don't know why they changed the word, introducing this scrambling. But so they say that this property, actually, this is the abstract of this. We show that the parametrically long exponential growth of out-of-time order correlator, also known as scrambling, does not necessitate chaos. So we propose the notion of scrambling be distinguished from that of chaos. So they say, okay, you can have exponential instability, but this is not related to chaos. So you see, there are some problem, as you see, and so I want to discuss this. Let us come back first to this paper by Bunimovich, Galinsky, Rosenbaum. So what they do, you see, they take this polygon. You see, the black line is a polygon. So you consider a billiard in a polygon. As I said before, this system has 0 Lyapunov exponent. It is not known. Mathematicians do not know about other like ergodicity, mixing, Mikl mixing. It is very difficult to prove theorem here, but it is known by theorem that Lyapunov exponent is 0. This is clear. But then they consider this they call mathematical billiard. Yeah, in a billiard for a point particle, they make an interesting observation that if instead of a billiard you take some circle of some radius r, no matter how small but non-zero, finite, then this circle, this disk, see a billiard, see the blue billiard, you see, because when it here still you have a vertex, but when you arrive at this corner, the billiard see this curve, it becomes rounded. So now you are in presence the blue line of a billiard, and this billiard with this curvature is chaotic. It is positively Lyapunov exponent. And you see, they consider this physical billiard because it is interesting, because when you do quantum mechanics, you start with a packet of finite size. No matter how small, you have some size, order of the square root of h bar, if you take some coherent state. And so basically, the quantum system see the curve billiard. So you expect that if you solve quantum motion inside such a polygonal billiard, you will find exponential stability. Yeah. And this is interesting and correct observation. So they do this. They try to prove, to show this idea that is correct. And so how to do? They do the standard thing. They take an initial wave packet, and then they with some width, which correspond to some circle in classical mechanics with some radius, and then they compute the OTOC, which is called C of t. So I'm reporting their work, yeah? And so as operator, they take position and momentum. So as you see, if you define OTOC in this way, this quantity probes the sensitivity of classical trajectory to initial condition, because momentum is derived to x. So if you insert here, you get C of t become this expression, which you see, it measures, you see, the separate this quantity. You expect that this quantity will behave like for the billiard will increase exponentially, will give you the Lyapunov exponent. Yeah. So we expect this quantity to increase in time according to this law. And instead of Lyapunov exponent here, there is a factor 2 because you have the square of this. Yeah. So you expect this if you compute this quantity. So exponential growth of OTOC, obviously, you expect this grow only up to the Ehrenfest time scale. After Ehrenfest time scale, then the quantum OTOC will saturate, so it doesn't matter. But for short time, you expect exponential increase with Lyapunov exponent. So this is the expectation. So what they do, also you can define a classical analog of OTOC. Instead of computing this C, you computed this quantity, delta x t over delta x 0, meaning the separation of orbit. You take average over the region corresponding to the initial quantum packet. And so this quantity should be the limit you expect will converge the quantum OTOC when you let h bar go to 0, if correspondence principle is valid. So they do a computation, and this is the result they get. So this is logarithm of OTOC. And you see, it is interesting then this one case, this is considered the polygon with r equals 0, not the rounded one, the mathematical billiard, we say. Here they consider the physical billiard in which the vertex are rounded. And you see the growth of OTOC is the same. And this is expected because the quantum packet, since it has finite size, in any case, you will see around the corner. So it will grow exponentially, even if it is a polygon and with some rate. And this is the result, which is expected, it is confirmed. But the main figure of this paper is this one, you see. Is this one in which they plot the logarithm of OTOC as a function of time for different h bar. So they take a polygon, they compute OTOC as I told before, and then they change h bar. So this is 2 to the minus 6, they get the grow rate, and then they decrease h bar, they get this, they decrease again, and they get this. So you see, there is an exponential growth of OTOC, which is due to the finite size of the packet, but you decrease the size of the packet and the rate doesn't go to 0. Actually, it increases. And so this is a clear breakdown of the classical quantum correspondence principle. Because in classical mechanics, when h bar go to 0, OTOC does not increase. There is no exponential increase, it's linear. So you should observe some horizontal line here. Instead, as h bar go to 0, this increases. So this is the main content of their work, and obviously numerical computation are correct. And personally, I was very surprised by this because I have in mind another quotation again of Max Hammer, where he said that in fact there was rarely in the history of physics a comprehensive theory which owed so much to one principle as quantum mechanics owed to the Bohr correspondence principle. So to state that there are some situations in which correspondence principle is no more valid is I mean, it's something I could not understand easily. On the other hand, there is a clear numerical evidence. So I started thinking about this if there is a way out of this situation. And indeed there is. We can show that there is no breakdown in spite of the result, which are above result, which I show which are correct. There are no breakdown in the correspondence principle, and the initial growth of the quantum autok instead goes over smoothly into the classical one. And the agreement as expected takes place up to time, which increase as its bar go to zero in accordance with the correspondence principle. So this is what we started to think about, and this is what is we managed to show. So how it is possible, so to show this clearly, well, we consider a simple system, a system like the billiard in a polygon, but which is simple. We consider this triangle map, which has the same property as the polygon. Actually, this map is an area, area preserving map to the square minus 1 plus 1 into itself. It is a piecewise linear potential because potential is just x, so it's linear, it is the modulus, so it's piecewise linear. Actually, we put beta equals 0, it doesn't matter, so it is very simple. So this map is a parabolic map in the sense, which means that the instability here is only linear. So it is quite simple. Also, it is quite simple to numerically iterate. Also, you can, so this map is, the potential is represented, modulo of x is this blue line. But you can do the same like for billiard. You can round off the corner here, 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 with some circle of radius r. Yeah, you can round off. So if instead of the potential modulo of x, you take the round off potential, again, like the billiard, the system becomes chaotic, exponentially unstable. If you round off with some r different from 0. Actually, in this case, we can even compute analytically the Lyapunov exponent as a function of round off r. And this is Lyapunov exponent as a function of r. It increases. And when r goes to 0, as expected, you go to 0 Lyapunov exponent, which is the limit of this our map. So, okay. But you must keep in mind another property of this map. When you round off the corner, the stability in the map becomes exponential because of this round off. Yeah, and so it is near this round off point, x equals 0, near x equals 1, where there are round off, that stability become exponential. And so you may understand it is intuitive that the local Lyapunov exponent will fluctuate. Yeah, it will become large near this round off point, and we can even estimate analytically you can see in the paper the analytical derivation, what is called maximal Lyapunov exponent near the round off point. Good. So again, we can do the same. We can repeat for our system the same as done for the triangle. The difference is that here the numerical computations are much simpler. You can do much better because you have a simple map. So again, we have the map over one period, which is a Floquet operator, and you can write the autok like with the same variable x and p. We can take an initial coherent state, and then we can solve quantum and classical motion. Also, okay, and this is the result. The results are the same as the Bunimovic paper. You see, we compute the autok for 3 different h-bar, like in the Bunimovic paper. For the case r equals 0, or to the -6 is the same, but let's say r equals 0. And you see, as you decrease h-bar, this slope increases. So it looks like when h-bar go to 0, again, you have a violation of correspondence principle, because in the limit, h-bar equals 0, the map has 0 Lyapunov exponent. While if you take for finite h-bar, you find positive, and the rate increase by decreasing h-bar. So again, it looks like that there is indeed a violation here, like for the billiard, a violation of the correspondence principle. But look what is happening. It's happening the following. Here is the same picture, but with decrease more h bar, yeah? So in the previous picture, h bar is what, 10 to the minus 6 minus 7, 2 to the minus 6 minus 7 minus 8. But here we take 2 to the minus 13, minus 15, etc. Down, we managed to go to 2 to the minus 22. And you see, as you decrease h bar, the growth rate decrease and goes to 0. And this is in agreement with the correspondence principle. So the rate which we have seen to increase with decreasing h bar, vanishing instead when h bar go to 0 in accordance with the correspondence principle. So here you may wonder what is happening, because it is strange situation, you see, because you start with some h bar, you decrease h bar and the rate increases, and then for some reason it start decreasing and go to 0 according to the correspondence principle. So there is a kind of non-monotonous behavior, very strange non-monotonous behavior as a function of h bar. Obviously, in the paper on the triangle, on the billiard, they could not decrease h bar in this way because it is impossible. You cannot do numerically on billiard. It will be is out of possible of present computer possibilities. But for the map you can do, because it's extremely simpler, and you can show what is happening. There is this. So how it appears that this non-monotonic behavior completely unexpected, these things. And so we understood this. And to understand this, first of all, in this case also you can compute the classical autoc in the sense that instead of commutator, you substitute with Poisson bracket. And so you get this ILC, which is the classical autoc. You have the logarithm of the integral here, so the logarithm of the average. Again, you start initially with the Gaussian distribution and so on. So if you round off the potential, again, if R is larger than 0, then there is no question. Everything is clear, both in classical case and in quantum case. You have exponential increase at initial time, and they agree, so there is a validity of correspondence principle and so on. Yeah, so there is no problem. The problem arises, as was pointed out by the paper by Bonimouch et al., when R equals 0, or when you have polygons. So to understand this, you can do the following. Look, instead of computing the logarithm of the average, you define this quantity in which you have the average, the integral of the logarithm. This is way you do when you compute in classical mechanics the Lyapunov exponent, yeah, because you take two orbits, you compute the rate at which they separate, you take the logarithm, and then you average the different Lyapunov exponent. So if you do this, you get again 2 times Lyapunov exponent because you have the square. So this is we compute this quantity L. Now the autoc, which you have defined before, it is close, almost the same as this quantity, which increases Lyapunov exponent, only if fluctuation of the local Lyapunov exponent from trajectory to trajectory are small. So I told you that if you compute the instability, the instability becomes large when you are near to the round off point. Yeah, so there are strong fluctuation. So if these fluctuations are small, then these two quantities are more or less the same. But otherwise, they can become, for small r, the fluctuation can become large, and they can dominate. And what they dominate, orbit which dominate the one with the largest Lyapunov exponent. So here, well, I don't want you lose the line. Don't be confused. So what you can show is that you can compute this is the classical autoc. It turns out because of this that the classical autoc increase like the Lyapunov exponent for t less than t star, and after it increase according to another parameter, which is lambda star. And the reason is what I told you, because if you take, you see, if you take an initial packet, if the packet is very small, then the orbits stay together and fluctuation remains small up to a long time. If the packet becomes smaller and smaller, this time T star become larger and larger. Actually, you see, it increases HC, it means H classical, is the width of the classical packet. Yeah. So if you decrease the width of the classical packet, fluctuation becomes are small up to this time. Yeah. But after T star, the packet become large enough, and then fluctuation become very large because different orbit inside the packet hit the different side of the corner. Yeah. So the net result is this one. That okay. So this is a numerical check of what I told you in classical mechanics. In the classical map, you see this is the auto classical auto. This is time. This orange line is the Lyapunov exponent. Instead, this one is lambda star. So you see, if the size of the packet is very small, here is 2 to the minus 39, yeah, it's very small, then you see that the packet follow Lyapunov exponent for a very long time. Up to T star is very large, because T star it goes like 1 over square root of the size of the packet. And then it increases like lambda star. But if you increase the size of the packet, for example, 2 to the minus 9, then you see practically the growth is always lambda star. It's not the Lyapunov exponent because of fluctuation. You see? And so for this reason, this is the reason why, so this explains the non-monotonous behavior of Auto as a function of H bar. Yeah, because in quantum, as for the classical case, we have a growth rate, which is 2 times Lyapunov exponent up to T star. And then after T star, you have increased lambda star. So the initial growth rate of Auto is determined by the fluctuation in the local Lyapunov exponent for large H bar, by the Lyapunov exponent for small H bar. Okay, so for small H bar, you get the Lyapunov exponent, but for not small H bar, you get lambda star. So the Auto growth rate, which was found in this PRL to increase the decrease H bar, is not given by is not the Lyapunov exponent, the growth rate. This is a point. It was not possible to imagine this. This rate is not the Lyapunov exponent. It is another quantity which can be computed. It is lambda star. So this explains why, if you still decrease H bar, then the growth rate start decreasing and go back, and you recover the correspondence principle. So everything is correct. There is no contradiction, and all the computations are correct, but the interpretation is this one. So, and correspondence principle remain valid. So this is the message I want to say, because otherwise people get confused. And also the other point I want to mention, the other result which ought to lead to some confusion is the paper I mentioned to you before. Yeah, that they propose that Auto is not connected to exponential instability, but this is again is due to the same reason as I explained before, because if you take an integrable system in which the Lyapunov exponent is 0, but integral system have isolated unstable points. They fixed isolated unstable points, and if the quantum packet go near this point, then there is fluctuation in the growth rate, and then you get positive Lyapunov exponent. What you have to do in order to solve this problem, you don't have to take the logarithm, the logarithm of the average, but to take the average of the logarithms, because this is the way in which you can suppress the fluctuation in the exponential instability rate due to this unstable fixed point. So everything, again, if you do this, also this is correct. So at the end, and this is the message, the correspondence principle is restored, there's no problem, and dot remain a useful diagnosis for chaotic dynamics, provided you have to be careful how you make the averages. So this is basically the message I wanted to say. Maybe I was quite fast, but then if you have a question, you can ask. Now, I wanted to tell another point, but I don't know if you have time or if I should stop. This you tell me.
please, you can keep going.
No, I will mention another a question about entanglement. So if you want, I can very briefly mention the thing, or I can stop here. So please let me know what. Okay,
So maybe more 10 minutes.
Okay, fine. Okay, well, I can do very short, but because I think it is an interesting point. Let me see. But there was a paper on Nature in which they measure entanglement, and they claim that this is distinguished between chaos and non-chaos in classical systems. So they do some measurement. In some system with divided phase space, and so they measure entanglement looking cesium atom, and then they found that when the system goes into the stable region of phase space, the entanglement decreases. This is a result of measurement, and in chaotic region is larger. So this is experimental result, which is correct, by the way. But the question is again about the interpretation. And so to show this, we consider the following problem. We consider I tell you very shortly, but the question is very simple. Take two particles, the total lattice with two particles, yeah, in one dimension. So you know that total lattice, if the mass of the particle are equal, the system is integrable. And but if you take different masses, the system has a transition to chaos. By the way, this is one of my first paper almost 50 years ago. It was published in 75. So this it refers to the total lattice. So now we have a system which can be completely integrable when two masses are equal, or it can be chaotic when the masses are different. And these are the phase space, okay? So when it's integral, the phase space you see is all related in tori. When you take different masses, the phase space becomes mostly chaotic. Okay, so this is a simple model, nothing strange. But now you want to compute, you have two particles, you want to compute how entanglement generate by the dynamic in this system. Now, okay, so what you can do, you start with the coherent state, separable. So time t equals 0 is disentangled. You compute, solve the Schrödinger equation numerically. It's very simple, you can do. Then you trace out particle 2, you get rho 1, the reduced density matrix, and then you write this quantity, which is the von Neumann entropy, which is a measure of entanglement. Okay? So here is how entanglement generates. So at time t equals 0, the entanglement is 0 because it's separable state. As you dynamics evolve, the two particles interact, so entanglement is generated. And here is the value of entanglement as a function of time. One is for chaotic and one is for integral. So first of all, you notice that more or less you don't see big distinction. But then you notice some feature. First, there's some oscillation. This oscillation, maybe they look periodic somehow. And the question is, so first of all, you wonder whether you can understand this. So I can ask you first a question to which I don't expect you give the correct answer, because anytime I ask to people, they give the answer not correct. Actually, when we started this work, also we started with wrong assumption, which is the following. Suppose you fix time, and this is h bar equals 0,2. So at this time, for example, you get this value of entanglement. The question I ask is the following. Suppose I fix time and I decrease h bar. I go to the classical limit. How do you expect this point to move? Is there anyone in the audience that can answer? So I start from a separable state. I compute entanglement generated by the dynamics. I arrive to some point here, some fixed point at some time fixed. And then I do the same, but with a smaller h bar until I go to h bar equals 0. So with another h bar, we'll get another point here, yeah? So what will be your expectation? Well, I tell you what was our wrong expectation. Our wrong expectation was the following. If you take h bar go to 0, you go to the classical limit. In classical mechanics, there is no entanglement. So I expect that if you have a fixed time, decrease h bar, this curve will go down, 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 and will go to 0. This was our expectation. But then we did computation, and I show you the result. And let me check the time. Okay, 5 minutes to finish. And this, so this is for interval and chaotic. H bar is 0.2. This is interval, this is chaotic. Now I take a smaller h bar. Look, it doesn't decrease. It's the blue curve, is h bar is 0.1. You see, is this and this, there is no, actually it looks like almost the same up to some time. Then I decrease h bar again, 0.03. And it seems that at least up to some time, they converge to some limit curve. So you see entanglement. We cannot decrease further h bar because for numerical difficulty, you cannot take h bar smaller, at least you can small a bit, but not much. So how do you explain this? So you see, it seems that as you decrease h bar, the entanglement generation in this quite simple system, which can be interval or chaotic in both cases, it doesn't go to 0, but it seems to converge to some limit curve. What is this curve? Can you predict this? Can you understand this behavior? Obviously, it is done on a system, but what I'm saying is quite general because it's just some dynamical system. One thing we can do is the following, like we did. Suppose you go back to classical mechanics. You have a system, a classical system with 2 degrees of freedom. You take 10 to the 6 initial orbit at time t equals 0 in the same initial condition as the quantum packet, yeah, some distribution of point. And then you solve the orbit, you compute the orbit up to time t, and then at time t, you project the ensemble of points on the plane Q1, P1. Then you go into the plane Q1, P1, is a 2D space, you divide it in cell of some size delta, and then you compute this kind of Shannon entropy. So Wi is the number of orbits which fall in the cell I in the 2-dimensional grid corresponding to particle 1. Yeah? So you integrate the orbit, you project on the plane Q1, P1, you divide this plane in different cell, and you look how many orbits fall in each cell, you call Wi, and you compute this Boltzmann or Shannon entropy. And so this is a quantity which you compute according to classical mechanics, and then you can plot this quantity as a function of time. And then you get this curve. This is solution of classical mechanics for the interval case and for the chaotic case. And then here is the quantum, is the entanglement. So as you see, the entanglement tends to follow, to go to the limit classical curve as you decrease h bar. So it doesn't go to 0, but it doesn't go to this Shannon entropy as h bar go to 0. So this was a result that for us was not expected at the beginning, and is a point on which we are still working. I'm working now. Right now, I'm working to understand better this problem. And I want to say that also this oscillation of the entanglement, you can understand, and then I close my talk, you can understand by the fact that this oscillation are due to the caustic when the orbit moves. Take the interval system. The phase space is foliated in tori. You project on the Q1, P1 plane, but the orbit, it moves on the tori. And when it arrives on the caustic, the density becomes higher. Yeah? And so you can explain this oscillation by the motion of the orbit on the tori. Here, see here an example. So if you project the probability distribution at some time on the Q1, P1 plane, you see the orbit tend to accumulate on the caustic. See? So this is the explanation why we have oscillation in the classical Shannon entropy and also in quantum entanglement. But so this is just an introduction. I wanted to mention this problem because I want to say that we don't understand completely why there is this situation, and I think I can stop here. Yeah, at this point. So if you have questions, I can.
Okay.
Ah,
Thank you
ah,
very
by,
much.
by the way, this is the result of the, I can tell you, the result of the experiment published on Nature, in which you see, they start with the quantum packet in this chaotic region or in the interval region. And they found that entanglement decrease when you are in the interval region. And this is why they say they attribute this to the integrability as compared to chaos. So they say chaos give larger entanglement than interval case. But this is actually not really, I mean, the result is correct, but the interpretation is not really so, because if you take total lattice to particle, you take the completely interval situation, not chaos, and you move with the initial packet along this green line, again, you see this decrease of entanglement, you see. But this is not due to chaos, because this system is completely integrable. It's simply due to the fact that when you arrive here, you arrive near the center of this orbit, of this periodic orbit, and then you decrease the possibility for the orbit to go around all the phase space. So this is why you get this decrease in the entanglement. It's not due to chaos, but it's just due to this fact that you approach the center of the tori, this periodic orbit. Okay, I mean, but I realized that I went too far, but I just wanted to give an idea, just to raise the problem, yeah, because the reason why this is happening is not clear to us also now, yeah. Okay, so, thank you.
Okay. Thank you very much, Giulio, for the seminar. So we can move to the questions. And also, let's thank you.
Yeah. Yes.
So,
Hello.
any questions from? Yes, please go on.
Okay, I have a question.
Yeah.
Thank you, Giulio, very much for a very interesting talk. First question is just about the chronology. So you basically answered the problem of this experiment in 75 already, or is it a new study?
Which one?
About the entanglement.
Yes. No, 71. No. What do you mean 71?
Well, so your results of explanation of this the problem with the entanglement is the new result or 75?
No, sorry, no, it's not 70. No, sorry. 70 is when I first studied the dynamical property of the classical total lattice. No. This I just mentioned because it was one of my first interests to understand the classical property of the total lattice with different masses. At those time, it was nothing to do with entanglement. It was just classical mechanics. Okay. This paper is different. It's recent.
Yeah, it was rather joking. So my real question is about this lambda and lambda star.
Yes,
so
yes.
You're saying that lambda is the real Lyapunov exponent.
Yes, lambda is the.
What would be the definition of lambda star?
Lambda star, well, you have to take an orbit and you compute the local Lyapunov exponent. So there is some region near the vertex, near the curve vertex, yeah, where they are circumferential, in which lambda start fluctuating, become very large. So lambda star is computed in an area near the vertex, near x equals 0, near x equals 1. It is computed, near this region and this region. Because when the orbit bouncing here, the Lyapunov exponent is 0. Because we have a packet with some size. So if a packet is very small, it's just bouncing here, here, and here. But when the packet become large compared to this radius, some orbits go one side, some orbits go to the other side, and the exponential instability become very large suddenly, become discontinuous. So it's you have strong fluctuation in Lyapunov exponent. You see, and so we can compute this, and then you can get well, I don't know how I put this, but you can evaluate. You can evaluate this lambda star and T star. This is our estimation of this quantity. It is
I
explained.
understood also that lambda star you'll get if you do averaging first and then logarithm.
No. Well, yes, because when you have, since there is strong fluctuation, let us put the following. Suppose you speak only about classical. Suppose there is strong fluctuation in orbit separation. Yeah, the local Lyapunov exponent is for most orbit has some value, and for some few orbit has strong fluctuation. If you make first the average and then take the logarithm, you will have strong fluctuation. But if you make first the logarithm and then take the average, then the few orbits which fluctuate, they will be suppressed. So you get the correct result. Yes, so for example, when you have a system with many degrees of freedom, for example, if it is integrable, in which you know that the Lyapunov exponent is 0, if you compute auto and you want to get 0 Lyapunov exponent, this is what you have to do. You have to take the logarithm of the average. Because if you take the average logarithm, you will get positive Lyapunov exponent, even if it is integrable. And this you will get also if you do with the packet in classical mechanics. You see?
Okay, and I have another question. It's about the crossover scale, right? You have this time scale at which you pass from lambda to lambda star behavior.
Yes, yes.
So what is this crossover scale?
Yeah, this scale is this one. Yeah, we estimated this. Is when the packet become large enough and fluctuation become too large, so you go from lambda to lambda star. Basically, you can see this in this picture. This is classical picture. So you take a packet, you compute this quantity, and then you see the behavior. So you see that it goes like Lyapunov exponent, and then it deviates at some time T star, which increase as you decrease H bar. You see?
It is the size of the packet.
Case, when H is 2 to the minus 39, the packet is very, very small compared to the radius R. And so basically, for quite a long time, you get the Lyapunov exponent. It's like, it's morally, if you have a single orbit, you have a packet, but it's very small compared to R, and so you go like Lyapunov exponent. But when you arrive at this point, the system, the initial packet become large because of stability, and then you get the lambda star increase because you can begin to have fluctuation, because this quantity is not the is not the logarithm of the average, but is the average of the logarithm. See? Okay.
Okay, thank you.
Yeah.
Any further question? So I have one. I think I missed it. You mentioned average over initial states in the end in one of how this is done is.
No, I mean when I compute Lyapunov, because when you compute classical Lyapunov, because I want to compute Lyapunov exponent, but simulating the quantum result, to have classical auto. So I take several orbits inside, making an average in an area which correspond to the initial quantum packet, because I want to make comparison with a given H bar. So how to do this? Because I do quantum computation, I get some result. Yeah, I take some initial packet with some size. So in classical mechanics, what I do, I take orbits, I take many orbits, but I average the result inside an area which correspond to the size of the quantum packet, which I call HC. Just to make a comparison with the quantum system.
Okay.
It's just have an average, yeah.
So maybe we can thank you, Giulio. Thanks, Giulio, again.
Okay. Thank you. Thank you to you. Thank you.
So, thank you, everybody. So next week we'll have one more seminar. So yes.
Okay. Bye. Goodbye.
Thank you very much, Giulio.
Bye.